as a tape. It's much more versatile. You can do more with it. All right. Now a bit of comment here. Now the PDA, it might be non-deterministic, but that's not a problem. You just have an equivalent non-deterministic Turing machine that does the same thing. And we know from earlier sessions that it's possible to convert a non-deterministic Turing machine into a deterministic one. Okay? And so we do that, so we get yet another conversion. And so we still have our a deterministic Turing machine that could simulate the grammar. Right? So, but there's a difficulty. Your grammar may be such that some branches of the if you have a non-deterministic, well, let's see, you have a parse tree in grammar, right? Okay, some of the branches of your parse tree. Remember, the parse tree just is it's sort of like a history of the computation of the derivations as your intermediate strings keep getting overwritten. The variables in those strings keep getting overwritten, and they get substituted by the right-hand sides of substitution rules, until eventually at the bottom, at the leaf of a branch, you get a string that consists entirely of terminal symbols. Right? Now, it's possible, depending on the rules, the substitution rules in your grammar, you may get a branch of that tree that just goes on forever. It just never ends up with a string that consists entirely of terminal symbols. That's possible. Right? You may get kinds of looping things where variable A goes to B and then B goes to A and stuff like that. Crazy stuff. But the point is, it is possible in a parse tree to have some branches go on forever. Okay? So if you had a Turing machine that's simulating a grammar that has a branch or one or more that goes on forever, then that Turing machine would just go down that branch and never halt. Now, if a Turing machine never halts, that's called looping, right? And loopers, I've not used that term before, a useful term. So a looping Turing machine is not, by definition, is not a decider, right? Deciders, by definition, are Turing machines that halt. And a halting Turing machine either accepts a string, its input string. Turing machines always have input strings. So it either accepts its input string or it rejects its input string. And that's it. That's what deciders do, no matter what the string is. Okay? It either accepts or rejects. Whereas a Turing machine that loops, like this third possibility, looping just means it goes on forever. And if your Turing machine is simulating a grammar that has branches, in the derivation tree, in the parse tree, that has branches that go on forever, well, that Turing machine is going to hang, right? It's just not going to make a decision, yes or no. It's not going to say. It's not going to reject or accept. It's just going to keep calculating. It's looping, and that's not what you want. That will not be a decider. See, if we want to show a language is decidable, well, the Turing machine has to decide, right? Well, if it's looping, it can't decide. It's not a decider. Okay, so that's out. So we've got a problem here. So we have to change idea, change direction somehow. Okay, that's what we're talking about. The non-halting. So we need a different idea, right? So an alternative idea is to. Oh, I've written it twice. Damn. Okay, is to go back to two theorems back, so 4.7, page 172 in your text, and where we created the Turing machine S, and we're going to a bit of a reminder. What does that Turing machine do? Just theorem numbers and page numbers don't mean anything. There's so many theorems and page numbers you forget. So a bit of a reminder. What does this Turing machine S, labeled S, what does it do? Well, its task is to take a grammar G and to answer yes or no whether some string W can be generated by that grammar G. Right? That's all it is. It's just this Turing machine, this algorithm, tests whether this grammar can generate this string W. Right? Now, that Turing machine S, we're going to we'll make it a component of a larger Turing machine called MG, M for machine and capital G for grammar. Okay? And we'll use that in a fairly simple algorithm that actually works. And here's how it works. Let's see. Okay, so you've got a grammar G, which is just a context-free grammar. Okay. For the language A, where's A? What is A? What is A? Is it this one? Okay, so A is this, right? I assume. Wait a minute. No, sorry, that's a grammar. No, that's the... Oh, I'm getting confused. What is A? I can just avoid the problem. So a grammar generates a language. Okay, so just call the language A, and that's the language generated by the grammar. All right. Okay. So it's just the language. I assume it's the language just generated by this grammar G. Okay. And we're to design, by construction, proof by construction, which is to design a Turing machine called MG here that decides that language A. And what is that language? It's a context-free language. It's a CFL. Okay? And that language is generated by grammar, as always. And what's the grammar? Well, it's a particular grammar called G. Whatever. Just some context-free grammar. That grammar generates the language A. That makes sense. Okay, so we're going to use as a kind of subroutine, a component, if you like, a part of this Turing machine, bigger Turing machine MG. We're going, as I was saying before, we're going to use the Turing machine S that will take a given grammar G and a given string and see whether this grammar can generate that string W. Alright? So here's it's pretty simple, in concept at least. You have the standard format description of an algorithm, in other words, a Turing machine. God, I always forget, it's amazing. Final code. The first line is some input, a description of your input string. Well, in this case it's W, and what's W? W would be a member of your language, A. Alright? And it could be any W. Right? Oh, wait a minute, hold on. W is just a string. It's a random string. Yeah, that's important. This is any string, okay? You're not given any constraints on the nature of this string. So you just got some string W. And if this is a context-free language, then if the W belongs to this language, if that's true, then the grammar G will generate that language. And how do you test that? Well, you use the Turing machine S. That's what that Turing machine does, right? From two theorems back. It input that machine S, Turing machine S. It inputs this string, formatted string, encoded string, G, W, and it accepts if this grammar generates that string W. All right, so we'll use that, and so we'll run the thing. Now, if the machine S accepts this, okay, we'll then have MG accept. Pretty trivial, right? Okay, but if this machine S rejects, in other words, this string W cannot be generated by this grammar, well then this W here, this string, does not belong to this language. Okay, A, and that's fine. So if this rejects, we'll then have machine reject. And what's this machine doing? Well, it's